This is Calculus 12, Chapter 5.5. We're going to be looking at more numerical methods to give us better approximations of area or definite integrals. First, we'll start off with a trapezoidal rule. It's a little bit more efficient than RAM. It's better to use approximate methods that have better estimates with smaller n's. This reduces numerical errors and computes quicker. Let's look at the trapezoidal rule. So to approximate the definite integral from a to b of f of x, the trapezoidal rule is h over 2 y naught plus 2y1 plus 2y2 plus dot 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 plus 2yn minus 1 plus yn. Okay, and to see this, we'll just look at a small curve like this. Okay, so we can estimate a trapezoid like that, like that, like that, and like that. Okay, this trapezoid uses this left endpoint. Why not? This doesn't have to be 0. This could be 5, 6, 7, 8, 9. Why not just means the first y value. Okay, so the first y value. And then for this first trapezoid, we use y1. And then for the second trapezoid, we use y1 and y2. So that's why we have 2y1. And then again, we have 2y2s, 2y3s. And for the last trapezoid, we're using the y3 from here and a y4. And we only use a y4 once. So that's why we just have yn at the end. You can see that a trapezoid is better than a rectangle because the amount of area that differs is smaller. So where a to b is partitioned into n subintervals of equal lengths. And they call this h, really it's a width, but that's the convention. So it's b minus a over n. And from our RAM calculations, we can actually calculate the trapezoidal rule. It's just LRAM of n partitions plus RRAM of n partitions over 2. So you can just use your RAM program to calculate the trapezoidal rule. You don't need another program. And again, LRAM and RRAM are the Riemann sums using the left and right endpoints respectively for the partitions. Okay, let's look at an example. And this is from the textbook, exercise number 2. We're integrating from 0 to 2 of x squared dx. We're using 4 partitions. So we take, this is b, and this is a. We have b minus a, that's 2 minus 0, divided by 4. So the width is a half. So the trapezoidal rule is 1/2 divided by 2. And we have 0 plus 2 times a quarter plus 2 times 1 plus 2 times 9 over 4 plus 4. Okay, I'm getting these values from here. F of 0, f of a half, f of 1, f of 3 over 2, f of 2. Because these are the equal partitions. And these are just the y values. And going in there. And we do a bit of arithmetic, and we get 1/4 times 44 over 4. And this is just 11 over 4. Try the calculation yourself to make sure you can reproduce it. Okay, part B says, determine whether it's an overestimate or an underestimate. So we take the first derivative. We take the second derivative. This is concave up, so it's an overestimate. And we'll exaggerate this. So x squared looks something like that. If we have a trapezoid, we can see that this is concave up, and it's calculating an area like this. And our trapezoid is bigger than this area under the curve. So it's an overestimate. Let's verify this with a definite integral in part C. So we do the antiderivative. This is x cubed over 3, and we're evaluating from 0 to 2. This is 8 over 3 minus 0, so this is just 8 over 3. We have 11 over 4, and we're comparing it to 8 over 3. We need a common denominator to do this, so we multiply by 4 over 4. We get 32 over 12. We multiply this by 3 over 3. We get 33 over 12. So this is bigger than this, so clearly it's an overestimate. Okay, we've been estimating areas under the curve, and what we deal with are mostly curves. And we're estimating with linear objects, so rectangles and trapezoids. So to get a better estimate, we should use something that curves. And that's where Simpsons rules come in. It's a better approximation for curves because it uses parabolas to calculate the areas. And to approximate it, we have this formula. S equals h over 3 times y naught plus 4y1 plus 2y2 plus 4y3 plus plus 2yn minus 2 plus 4yn minus 1 plus yn. Okay, so we alternate between 4s and 2s. The second last term has to be a 4. And because of this pattern, it has to be partitioned into an even number of subintervals. And the subintervals, again, have the length of h equals b minus a over n. So let's do this approximation. We'll start off with our old approximations. We're going to integrate 1 over x, and we're going to use LRAM, MRAM, RRAM, T, and S with n equal to 8. And then we're going to just calculate the definite integral. So you know how to do this, so I'm not going to explain this again. We get 0.725 for LRAM, we get 0.6926 MRAM, we get 0.6628 with RRAM. And to calculate TRAM, we add these two up and divide it by 2, and we get 0.69412. So you can see that these, they don't converge much. It's by 0.03, and that's with an n of 8. Okay, so h equals b minus a over n. So we have 2 minus 1 over 8. So that's 1 over 8. So to calculate Simpson's rule, S equals h over 3. And we're doing f of 8 over 8. So each width is 8 over 8. Plus 4 times f of the next point is 9 over 8. Plus 2 f 10 over 8. We're just adding an eighth each time. 4 f 11 over 8 plus 2f 12 over 8. And I'm not simplifying it here because we wanted to see the progression. Plus 4f 13 over 8 plus 2f 14 over 8 plus 4f 15 over 8 and plus f 16 over 8. We have 1/8 divided by 3. And fortunately, 1 over x is an easy function. So we have 8 over 8 plus 4, 8 over 9 plus 2, 8 over 10 plus 4, 8 over 11 plus 2, 8 over 12 plus 4, 8 over 13 plus 2, 8 over 14 plus 4, 8 over 15 plus 8 over 16. And you can plug that into a calculator relatively easily and quickly. So this is 1 over 24 times 16.63570874. This gives us an approximation of 0.69315453. Now let's compute the definite integral from 1 to 2, 1 over x. And you should recall that the antiderivative of this is ln x. And we're calculating from 1 to 2. So this is ln 2 minus ln 1. And ln 1 is 0, so we just have ln 2. And that's approximately 0.69314718. Okay, need lots of room to get an accurate number so we can get the proper percentage errors. And when we're calculating percentage error, it's 100% times our estimate minus our actual value divided by our actual value. And this is 4.648%, 4.369%, 0.0713%, 0.1394%. So the trapezoidal rule is not always the most accurate. MRAM is pretty good sometimes, and sometimes trapezoidal will be better. And for our Simpsons rule, 0.0011%. So that is a very good estimate, given that we're only doing 8 partitions. And lastly, we can use the trapezoidal rule or Simpsons rule on table of values, just as easily as on a function. So when we're looking at the table of values, we take one value, subtract it from the next value to get our width. So 0.5 minus 0 is 0.5. So I won't bore you with just all the copying details. So we have h over 3, v0, 4 times v of 0.5, 2 times v of 1, and so on all the way to v of 5, okay? And then we just substitute the values. We do our calculations. We get 1/6 of 268.41, and that's roughly 44.735, and that's meters. Our table is meters per second. We're integrating seconds, so we end up with meters. And that completes this lesson.